logarithmic functions. So what is the inverse of an exponential function? So if we have some function y equals 2 to the x, and we want to find the inverse, remember, in order to find the inverse, we switch the x and the y. So we would say x equals 2 to the y power, and then we would need to solve for y. So how would we solve for y? How would we get that exponent down? The answer is logs. The inverse of an exponential function is called a logarithmic function. It's written as y equals log base a of x. The logarithmic function y equals log base a of x, where a is greater than 0 and does not equal 1, is the inverse of the exponential function y equals a to the x. So y equals log a of x if and only if x equals a to the y. So the base here in your log is the base here of your exponent. The exponent here gets spit out of the log. The purpose of the log is to get that exponent down. So that will get the exponent by itself. And then what your exponential function is equal to is the argument of your log. Each logarithmic equation corresponds to an equivalent exponential equation. So that's this, what we just said. So write each equation in exponential form. Log 125 of 25 equals 2/3. So the 125 is your base, the 2/3 is your exponent, and it's equal to 25. Log base 8 of 2 equals 1/3. The 8 is your base, the 1/3 is your power, and it's equal to 2. Write each equation in logarithmic form. Right, so this time the base of the exponent is the base of your log. The 64 here is going to be the argument, and the log should always equal the exponent. So the 3 should be by itself. Here, 3 to the negative 3 equals 1/27. The 3 here is the base of our log. The argument is the 1/27, and the power, -3, is what it's equal to. So that goes over here, and that goes over here. Evaluate the expression log base 7 of 1/49. So in order to be able to put things in switch between log and exponent form, we need to have an equation. So to make this an equation, we're just going to set it equal to x, and we're going to solve for x. If we put this in exponent form now, this is 7 to the x power equals 1/49. 7 squared equals 49, so 7 to the -2 is going to be 1/49. So we get that x equals -2. Radioactive materials decay or change to a non-radioactive material in a predictable way. Archaeologists use the decaying property of carbon-14 in dating artifacts like dinosaur bones. Geologists use thorium-230 in determining the age of rock formations, and medical researchers conducting tests use arsenic-74. A radioactive material's half-life is the time it takes for half of a given amount of material to decay and can range from less than a second to billions of years. Radioactive decay can be modeled by the equation n equals n0 1/2 to the t over h, where n is the final amount of the substance, n0 is the initial amount, t is the time, and h is the half-life of the substance. So how long would it take for 256,000 grams of thorium-234 with a half-life of 25 days to decay to 1,000 grams? So 1,000 grams is our final amount. 256,000 is our initial amount. We don't know T. We are solving for T. H is 25 days. So first of all, we need to divide by 256,000. And we can just simplify this by canceling some zeros and make this 1 over 256 equals 1/2 to the T over 25. So now we can write this in log form. This would be a log with a base of 1/2. Our argument is going to be 1 over 256, and that's going to be equal to T over 25. And then we can multiply both sides by 25 and get that T is equal to 25 log base 1/2 of 1 over 256, which is 25 times log base 1/2 of 1 over 256. And that ends up being 200 days. We know it's in days because our half-life is also in days. Properties of logs. If m and n are positive numbers, b is a positive number other than 1, and p is any real number, the following properties hold. If we have two things multiplied together inside the log, we can split that up into two separate logs and we add them. So log base 3 of 9x, 9 times x, we split that up into log base 3 of 9 plus log base 3 of x. For division, if they're divided inside the log, we split that up and we subtract them. So log base 1/4 of 4/5 is log base 1/4 of 4 minus log base 1/4 of 5. If we have an exponent inside the log, we can bring that out front. So log base 2 of 8 to the x power, we can bring that x out front and make that x times log 2 of 8. And if we have two logs with the same base that are equal to each other, then their arguments must also be the same. So log 8 of 3x minus 4 equals log 8 of 5x plus 2. That means that 3x minus 4 equals 5x plus 2. So, solve each equation. Want to solve this for p. First of all, I'm going to take this 1/3 out and make this 1/3 log p of 64 equals 1/2. And go ahead and get rid of that by multiplying that by 3. So we get log base p of 64 equals 3/2. Now we can switch this to exponent form. We're going to get p to the 3/2 power equals 64. To solve for p, we raise that to the 2/3 power. The 3's cancel out and the 2's cancel out. And 64 to the 2/3, the cube root of 64 is 4, squared is 16. Log 4 of 2x plus 11 equals log 4 of 5x minus 4. We can just cancel these log 4's out and just say 2x plus 11 equals 5x minus 4. And that's easy enough to solve. We subtract 2x from both sides. We add 4 to both sides. We get 15 is 3x and x equals 5. We do want to plug that back in and make sure that we don't get any negatives in our arguments. You cannot take the log of a negative, so you always need to check. But in this case, it looks like we get positive numbers in there, so that will be our correct answer. If we do get a negative somewhere, that means that we have an extraneous solution. Here, before we can cancel out these log base 11s, we need to combine these x and x plus 1. So we're going to make this log base 11 of x times x plus 1 equals log 11 of 6. Now we can cancel those out. I'm going to go ahead and distribute this x, make this x squared plus x equals 6. X squared plus x minus 6 equals 0. That's going to factor into x plus 3 and x minus 2, which means that x equals -3 or positive 2. Again, check. If I plug x minus 3 in here, I am going to get log base 11 of -3. So this is an extraneous solution. Extraneous solution. The only solution is x equals 2. And that's it for log rules. Stay tuned next time for how we can use these log rules for solving common logs without a calculator.